Yes, thank you. I guess almost everyone in this room has heard about this somewhat anonymous object until the news broke last week on Wednesday that Swiss astronomers, together with Portuguese astronomers, apparently have found a planet which is very much like our Earth, and that attracts a lot of interest because you start coming into philosophical thoughts. Might there be life there? Is there liquid water, and so forth? And the authors actually are speculating on this topic. So what I want to go over with you today is I want first to have a little examination of the observational evidence. What is actually fact? And then how these people have been interpreting these facts. Because, of course, normally you do some kind of interpretation when you are looking at empirical data. Then, of course, we want to know whether the hypotheses that bring forward eventually or in the near future can be tested by new experiments. And then I will have, finally, before we get to the beer and the wine, only one conclusion. Although it says conclusions. The object has a funny name, or funny, the somewhat odd name, Liseau 581c. The first question might be, why Liseau? Well, this is very simple. This was a German, or is a German astronomer, who made a catalogue of stars, the most nearby stars, all stars which are known within 25 parsecs from the Sun, that is, within about 75 light years or so. And actually the catalogue is called, Liseau, Bierweiss, or something like that, with another name. So normally you see, no, it must be with a J. Jarweiss. Normally you see nowadays the extended catalogue has the objects are not called GL, but they are actually called GJ. This is a more official name of the thing. But why 581? Yeah, it's simply the item or the entry number 581 in this catalogue. And why C? Is there an A? Is there a D? Is there a Z? Of course there is an A. But the A is never mentioned in this context, because the A, lowercase a, would be a planet, and that such a thing does not exist. It could be that you have a binary planet, then the primary would be lowercase a, and the secondary would be lowercase b. So normally for these extrasolar planets, you start with a capital B. And this derives from the fact that binary stars have had this nomenclature. Like Sirius A, capital A, is Sirius we see in the sky, Sirius B is a little tiny white dwarf companion. Now, obviously, if there is a C, then there might be perhaps also a Liseau 581b, which is yet another planet. Actually, that planet was the first one detected around this star, Liseau 581. And it has an estimated mass of about 16 Earth masses, which is close to a Neptune mass or something like that. And it is orbiting the star Liseau at a very close distance, at only 400ths of the separation between the Earth and the Sun. And actually there's still yet another one, which is called Liseau 581d. So there are at least 3 identified planets in the system according to these authors, the name of which you can see here. And you can see the thing B is about 16 Earth masses. The one which attracts our interest is about 5 Earth masses, and the other one is about 8 Earth masses. And they are all at distances which are very much closer than the Earth about the Sun. But the star is also much less luminous. And that is a point here. Now what they are doing, I think it's known what they are doing. The evidence stems or is built on the fact that one is looking at the star. One is never seeing any planet here. Okay? What one is looking is at the star, and you look at the spectrum of the star, and if you have a star-like spectrum, or a spectrum of a star, which is reminiscent of the sun, then you will have a lot of these absorption lines in this spectrum of the star, which arise in the photosphere of the star. And if the thing would be doing nothing, then you would always, whenever you look at it, you would have the spectrum. Now what is happening, what they observe is that the spectrum is going back and forth. And that is due to radial velocity shifts along the line of sight. That is, the thing is going back and forth. That is the interpretation of this. And here is actually shown the spectrum, the discovery spectrum or light curve, the radial velocity curve, of the first object ever, which is this 51 Pegasus, which was discovered in 1995. And that one is a very nice curve. It is what we call a real sine curve with no asymmetries in it, and that gives us the idea that the orbit of this object is circular. Very much like the Earth, but the object is much heavier than the Earth, and it is orbiting the star much closer in than the Earth. But there's only one planet, and that's a reasonable assumption of how to interpret the data, because you never saw this planet. Okay? I think it is important to remember that we never see the planet. In this case, which is another famous one, you see that the data already become a little bit less reliable, perhaps, but what you can see is that the curve is not a straight sine curve anymore, but it is somewhat distorted, so there's an asymmetry. And the interpretation of such a sine curve, or the way the data are fit with, is that this orbit of the planet is eccentric. It is not truly circular. And the eccentricity in this case is quite large, it's 0.2. There's no such planet in our own solar system with such an eccentricity. But still, they are fitted with one planet. And you can say, okay, so this is a reasonable interpretation of the data. Oh, sorry. I never had the chance to test it yet. Sorry. So I have to go back. I don't want to. That is what I wanted to show you. Now the data for Liseau 581 are shown here on the left and what's on the right. What one has been doing here is that one has observed such a radial velocity curve, that is all the thing is moving back and forth in time, and then fit various parameters of a sine-like curve to it. Then the fit is not perfect, so they get some residual when they derive the fit from the data, and then they see that the residual also has a sine-like behavior. So they fit it with another planet, and then subtract the residual, and again you get something, also the second residual, which looks like, perhaps like a sine-like curve, so they fit a third planet to it. Now the problem is, whenever you do this, you're introducing 5 new parameters. And 5 parameters to fit a planet is not a small thing. I mean, to those people who are doing fitting or modeling data, if you have 5 more parameters, I think one could say one could fit an elephant to such a thing. Now, you can see what the data really look at if you compress the thing in real time, and then you have a point here, a point there, then you have a lot of oscillations here, that is periods of these 3 pairs, and then you have a data point now and then. So I leave it to you, of course, to see how convincing the thing this is. I don't want to... Yeah, sorry.
Can I ask you about this previous plot? Does the plot for B contain already the entire fit, including C and D?
Sorry.
And how would it look like if you did only one of them? You see what I mean?
If you had only one of them,
Yeah.
it would likely, the previous one, when they discovered B, I think it would look something like that. Now they have extended the database, they have more points, so they can get a better chi-square, that is what it will. They make a chi-square minimization. Okay? So they get a residual from this stuff, and then, oh, this looks like another planet. And this is I would say, a normal thing to do in this business. There are several systems around, at least a dozen, where you have 3 planets in there. I don't know of any where you have 5 or 9 planets, or 8. 3, it seems to be where you hit the noise level, because of course this is noise bounded by a few meters per second, which is an extremely accurate. The data taking is really, this is something heroic what these people are doing. Maybe I should really underline this for those who are not astronomers. The data are excellent, but sometimes maybe one is overshooting in the interpretation. I don't know. You will see. We saw this one. Now, I don't want to go into formula, but it is a very straightforward thing to interpret this data by looking at this amplitude of the oscillation, and one gets out something which is a mass estimate. That is what is important. But the mass estimate is in units of this m sin I. And the sin I is not unimportant. It has to do, the I is the inclination of the system with respect to the line of sight. And as you can see here, you need actually 6 parameters in order to fit such a system in 3 dimensions. Now, the sin I, as you know, is bounded between 0 and 1. And 1 is fine, because then m sin I is m. And that is what these people are offering. 5.03, all 3 Earth masses, by suppressing the sin I. Okay? So the 0 you would have if you would see the system edge on, but then of course you don't have any radial velocity amplitude. It would be very, very small. If it is exactly pull on, there's no radial velocity, because you see the thing going around in a circle in the plane of the sky. There is no shift in this direction. So you need at least a little angle. If you see it from the equator plane or the plane of its motion about the star, then the sin I is 1, and then you get out the mass. Now, we don't know the inclination of the system, but if you look at the distribution of a randomized inclined system, then of course the sin I is 0.5, which means the angle is about 30 degrees, you see it. So for a random distribution, one would say, oh, we have to allow for a factor of 2, and the mass of the thing then is about 10 Earth masses. For me, that's fine. Why not 10 Earth masses? One of 11 or 8. I don't care. The problem comes into play, and this number was never shown in public, because if you see this number, then people say, oh, wow, wait. Now we are coming into tricky or murky, territory. Because at 10 Earth masses, this is a magic number in planet formation. And one theory, there are at least, or 2 main competing theories of how planetary systems are formed. And then one, perhaps the most popular and most widely distributed one, this is a magic number. Because once you have a body, a rocky body of 10 Earth masses, and it sits out in the disk of the solar nebula or the stellar nebula, it will accrete like hell. The gas which is around, it will become a gas giant. It will never stay as a 10 Earth mass rocky planet. That is the primary theory telling us. That's the way they make Jupiters. That's the way they make Saturns and Neptunes and so forth. And this theory actually has problems with making things which are much smaller than it. For the time which is available. Given infinite time, it's not a problem. So it is a borderline case, I think, if we have to assume that it might even be 5 times 2 Earth masses.
Sorry, a question.
Hmm.
Why shouldn't the average angle be 45 degrees for the system?
It is a distribution of sine, the
Yes,
average.
Yes, but why should sin I be uniformly distributed? I mean, it should be the angle that's uniformly distributed.
If you look at the probability distribution, you will find that it is 1/2 in the sine I. Yes. I was convinced of that by a mathematician once because I used 45 degrees. That's why I remember that it should be, sine I should be 30, or the international 30 degrees.
I mean, if you just take a random system,
Yes.
the expectation value would be 45 degrees, so then
What you look at is the distribution of P dt, of the probability of finding an object under a certain angle. And if you make the math, it turns surprisingly out to be sine I is 1/2 on the average. If you don't need to do this now. You can see, it doesn't matter if you take 45 degrees. It makes things not very much better, not very much worse. It's square root 2 about over 2 instead of 1/2.
Actually, if you go back to the previous slide, the magical number to an Earth masses is calculated for a solar type star. So around this small star, it should be even lower. So I think 5 Earth masses will already be
It's already, yeah, sure.
already
If
a
you take-
problem.
Yeah, sure. No, but I was thinking of, when I saw 10 Earth masses, then...
Yeah, it always rings a bell.
You agree on that one?
Oh, it's even worse.
So, in order to arrive at the true mass or the true radius, one would need something like that, where one has the planet going in front of the star, and you see a light curve. Oh, sorry. You see, I'm sorry that. So now here the planet comes into view. So we would see the system more or less edge on. There is very little room, of course that depends on the size of the planet, the size of the star, and so forth. What you could infer from that, but we can say that the system is inclined by at least more than 2 degrees. That is what we can say. You don't see it from the edge on, so sine I is not exactly 1. There is an observation of that. Okay? So we can't say very much more than this. Okay. But as you might know, there are also other methods which have given us actually planetary masses of the order of an Earth mass or a few Earth masses. And one of the very first detection of Earth mass planets were actually about an orbit about a pulsar. Another one was very famous in a paper by Liseau et al. Last year, where they used gravitational microlensing, and they gave an Earth mass of about 5, or a mass of about 5 Earth masses, with a reasonably large error. So another aspect of this planet was the idea about the temperature of the surface of this object. And the authors will say that for the known luminosity, which is the power the star is emitting, and if one is assuming an albedo, which is like that on Venus, then the surface temperature would be below 0. Whereas if the Earth's light albedo is more like that of the albedo is more like that of the Earth, then we would end up with 40 degrees or something like that. So they go on and say, let's assume that for a 1.5 Earth planet radius, then you would get about 20 degrees for 0.5. These are numbers just taken out of the air. And then in this context here, the conclusion is that GL581c is probably the most Earth-like of all known exoplanets, and that is what made all the excitement. Now, how do they get these numbers? I could ask, is this really correct what they're claiming? What they are doing is they're taking a very, very simple analysis here. And what comes into play here is the stellar luminosity, which is known, and from that, if you do an assumption that the thing is behaving, that the planet is radiating in a very simple way, then you will get these numbers. So when I do this exercise, I get numbers of +5 and +50, which is essentially the same. It really depends in the end on what you assume for this little guy, epsilon. I took an average which we have on the Earth, which is about 90%. If you take 8%, then this thing goes down to -2 and so forth. Now, if you do this, and now we can do this for what we know here on Earth, because then we can go out with a thermometer and measure the outside temperature. We don't have to guess it. We get, from this type of analysis, a temperature which means 250 K in absolute units. And what does it tell you? Oops, this is far below zero. And this is not what our daily experience is. The average temperature on the Earth is not below zero by that much. In that case, our oceans would be frozen all over, which we know they are not. And this is to do with that this analysis these people are doing here is simply much too simple. They are using something what we call black body as a radiator. The average temperature on Earth is larger than 0 Celsius because the Earth is not radiating as a black body. It's as simple as that. Now, things which are not radiating as black bodies are very, very hard to treat in astronomy. This is actually our daily bread. That is what we are doing most of the time. We are dealing with things which are not radiating as black bodies. That's what we get the research money for doing. Because otherwise, as I showed you, you can do the analysis on the back of a staff, and nobody's interested. Okay? So, the problem with this temperature determination, of course, lies in the fact what the albedo or the reflectivity is of the stuff. And here you can see on the Earth, this varies between about 5% to 85%, depending on what you're looking at, and how you average over the planet. Whether you have clouds, what kind of clouds there are, whether you're looking at the desert or at green stuff, and so forth.
Is this at any particular wavelength?
This is meant to be in the optical and the visual.
But broadly, it's what I'm speaking about. I mean, it's not one single wavelength. But
The stuff, in our case, in the Earth, the solar radiation is absorbed mainly in the ultraviolet, optical, and in the near infrared. Reprocessed and re-radiated to space or against the atmosphere in the infrared and far infrared. And that is exactly what is happening.
That's a measurement.
Yes. So what's happening is that you have what we call the greenhouse effect. We are, thanks to greenhouse gases in the Earth's atmosphere, on the safe side. So we should not be talking too badly about greenhouse gases. They are good also. Some of them are, these greenhouse gases are good. Now if you, the case which we know of, which is really extreme, is that of Venus, where this thing has, instead of about 20 degrees or so at the surface, the temperature has increased because of too much runaway greenhouse effect to more than 700 Kelvin, that is over 500 degrees Celsius. And now, these are cases which are close to us, where we can observe what is going on, whereas at Liseau 581c, we never saw the planet, so we don't know what's going on there. And the idea of whether we have temperatures which admit or permit water to be in the liquid state or not, I think is very premature to draw this conclusion at this stage. So how could we test this? Yeah, the only thing to do this, as far as I'm aware, is to not look at the star, but to look at the planet itself and see what kind of, whether A, it has an atmosphere, and what the atmosphere is made of. Here we have the three spectra in the infrared of Venus, Earth, and Mars. And you see that the greenhouse gas CO2 is very prominent in the spectra of the planet. This you will not see by looking at the sun. You have to look at the planet. So is there life on this thing? This is even going further in the speculation which has gone around the globe. And I don't know, nobody knows. But we can say, we can conjecture what were the conditions of life on a place like that. Now, this guy, Liseau 581, is a red dwarf star, and this perhaps Earth-like planet is very close in to the star. So these red dwarfs are known to expel huge flares at times, which might make this planet sterile and totally inhabitable. Now, this thing, it has actually a name, and I would be very, very much surprised if people would not call me René, but 4902 3051, my personal number. Why? Why are you doing this? Because this guy has a name. It's H.O. Libre. And what does it mean? It means it's a variable. And it's a B-Y Draconis variable. What is a B-Y Draconis variable? It's a star which is known to possess active regions, like stellar spots, which you see in the light curve very closely and very neatly see the star spots on this thing. And at times there are bright spots like here, and at other times there are dark spots as in the sun. So it is in a way, a parallel case to the sun, but much blown up. The variations normally do not exceed much more. The amplitude and the light variations are often not much more than, say, a factor of 3 or so. And what is modulated in the light curve is, of course, the rotation of the star. And that can be a tiny fraction of a month, can be up to a month, like in the solar case. It partially depends, I think, on the age of the star, because there is a relation that stellar rotation on these objects declines as they become older. There was nothing mentioned about the age of the star, and it's very difficult to assign ages to individual objects. There are various methods astronomers are using, and there is one paper on the age of the star. What the authors of the planet paper were pointing out was that this is one of the most quiescent M dwarfs in their sample, which could give you the idea that this is a rather mature object, because young M stars, they're very violent, and you would probably be in a situation like that, which is taken from the February issue of Astrobiology, this picture, which was a special issue on M dwarf habitability. What is more, perhaps, interesting in this case here is that if you look at the plot where we see the distance of the central star expressed in astronomical units, so this is the mean distance of the Earth from the Sun. Here is 1, here is the Sun up here, here's the Earth. Here's our solar system in this diagram. There is the solar mass here. This would be Venus, this would be Mercury, Mars, and so forth. Now this yellow scratched band here with some variable width is called the habitable zone, and it is defined primarily or uniquely by the claim that water has to be in its liquid state. And that you have this distribution simply reflects the fact that stars of different masses are producing different amounts of radiation output. And this relationship is not linear, so that's why you have this strange inclination, obviously. Now, another interesting line here, at least for me interesting, is this dotted line here, which is somewhat inclined and which is called the tidal lock radius. Now, this tidal locking, that is, two bodies which are in gravitational interaction with each other, are exchanging, if you wish, gravitational waves or gravitons or whatever, which makes them dependent of each other, like the moon in the case of the Earth. I think everybody knows here that the moon is in tidal lock with the Earth. It always shows us the same phase. Before the Russian and American spacecraft, we never had a clue of what the backside of the moon looked like, or the dark side of the moon, as Pink Floyd called it. Now we know, of course. And it looks actually different from the front side, surprisingly. I found it a bit surprising. And this could happen when the star also, because this planet is here, far in the tidal locker. This planet, given enough time, and I believe, given the evidence, the star is quiescent, it's not active, and given some other evidence, it is about as old as the solar system. This thing is definitely tidally locked to its star. So it will always show the same phase. And then, of course, it depends on whether it has an atmosphere, whether it can keep an atmosphere or not, what the temperature distribution would be. If there is no atmosphere, the hemisphere which is facing the star will be very hot because it's so close, and the radiation is similar to that on the Earth. And the other one, which is facing free space, will be very cold, like on Mercury, for instance.
I didn't understand your argument for why there would be a tidal lock. I mean, just the fact that you have a gravitation, that's not automatically give you a tidal lock, does it? I mean, the Earth is not showing.
No, but you always have some sort of force. Okay? And this assumes, I mean, it is based on, this is a rather lengthy discussion here, but it depends on what you assume, what the structure of the planet is, what's the inside is. Okay? And there is good reason to believe that such a big planet, mainly due to radiative decay, will have a liquid core, like the Earth. Well, that is what structure models tell us, right? So there will be some force.
But the fact that the moon is showing the same sign all the time, isn't that just a coincidence?
No.
It is a time.
And eventually the Earth will also end up in the same situation.
In 40 million years.
It's just that the Earth being the bigger guy, it will take more time. But first the small guy is locked, then the bigger guy is locked, because you exchange angular momentum. And the total angular momentum has to remain constant. So this is why the moon is going away from the Earth, because it's slowing down, the Earth is slowing down, and total angular momentum is conserved for the two spin angular momentum decrease while the orbital angular momentum increases. And in this case it's even worse, because the star is so much bigger than the planet that the planet will get lost much before the star.
We don't know, of course, right? So it is a reasonable conclusion based on the evidence we have that this thing would be tidally locked to the star. That it has a rotation, one rotational period would correspond to one orbital period.
But what was the distribution of distance for the planet? How?
The planet has been determined. How this is determined?
I mean the range of. Could it be twice as much, 3 times as much?
No, I think this is fairly well established once you know what you can establish. It's a period. Okay, you get from the radial velocity curve directly the period of this oscillation. And then, once you know the period, there is a unique relationship. And its very simplest form, which is called Kepler's law, and that is relating the period to the distance of the object. So I think this is a reasonably well-established number. And then I just put it in here by hand, and you see where it goes. It's even And I think that it's also fairly well established among planet guys that the planet is actually inside the habitable zone. Not really, which makes the temperature budget a little bit more or less favorable. So the question then is, which has been, or I have been gotten from journalists, is, shall we go and live there eventually? Right? And there are two answers to it. The one, maybe the temperature and the atmosphere is not good enough. But the other one is, what is it possible, right? Now, these are funny, stupid numbers, but I think it's still quite neat. Now, the fastest thing man could ever build so far is this Voyager 1 spacecraft, which recently has passed a distance of 100 times the Earth last year. And this one is going it has reached a speed which is 6 kilometers per second higher than the escape speed from the Earth. And it has achieved this speed by picking up, again, gravitational energy from Jupiter mainly, which is called a kick or a gravity assist. So it is sailing about by 17.2 kilometers per second. So how long does it take if it were on the way to H.O. Libre, how long would it take? Now we know what the distance is and so on. And at this speed, it would take, in roundish numbers, 350,000 years. If it were going at the escape speed from the Earth, it would take about 550,000 years. I mean, it's not a big difference, right? But still, it's a few 100,000 years. I will not go into arguing about travel at close to the speed of light, because this is not a physics problem, it's an energy problem, and you don't have any solution to it. Of course, if you could travel close to the speed of light, this would not take 350,000 years, of course. It's a very simple estimate, even in linear theory. Oops. Can you observe it? That it's a planet, and there are currently two proposals of what to do about to look at extrasolar planets. And one is a coronagraph type of mission, which is studied by NASA. And what you have is, it is called coronagraph because it has been used during solar eclipses by looking at the corona, or it is used during non-solar eclipses to look at the sun outer layers, such as the corona. And it is essentially, simply speaking, a little thin object which blocks the light from the star. Now, there are certain restrictions what you can do, and in this case, the planet is so close to the star that the maximum distance it would take during, when it is at maximum elongation from the star, would only be 10 milliarc seconds. And this is not what even the big version of the coronagraph of NASA would be able to do. However, there is this beautiful project called Darwin, which is an interferometer. And this thing is versatile. You can take the interferometer elements and put them anywhere you want. And it turns out, because this thing wants to take spectra of the kind I showed before to see whether there are greenhouse gases in the atmosphere, it will take simply 100 meters baseline to see this little envelope planet. And it will definitely do it. Of course, that is what these people were referring to in their article also. But when it's doing this simulated here, you see the stars disappearing and pop up the planets here, and you can take spectra of them. Or you do take spectra at the same time. Now, within the financial restrictions the European Space Agency has been facing, it had to come up with a plan how to distribute the little pieces of funding it has received, and came up with a brilliant plan which is called the Cosmic Vision 2015 to 2025. And people are proposing various space missions and scientific experiments in space to either for this. And for Darwin, there is a consortium of scientists which is proposing this kind of mission to ESA. What we would like is to have a broad and heavy support in the community throughout Europe. And if you are in favor of that we should be looking for planets outside the solar system and to see whether there is life on them, please send me an email and tell me that I can take your name and put it and forward it to ESA. Because I think these lists of these supporter lists are really important. I personally find it ridiculous. Anyway. Now there is, when it comes to this particular star, ESA 581, there is a little, which you can see here, actually. There is a little tricky thing here also for Darwin. This has to do with the fact that you might remember that Libra actually is one of the zodiacs. What does it mean? What is the zodiac? The zodiac is the projection of the Earth's orbital plane onto the sky plane. You can say it's just seen here. And there are 12 of these things. You know, some of you are Libras and others are Virgins and what have you. And that is by itself does not mean anything to an astronomer. But what it means is that the zodiac is, as I said, the essentially means that things are projected or outside the plane of the Earth about the Sun. And there we have also a lot of stuff, the so-called zodiacal dust. And zodiacal dust means that observing conditions are not very optimized. You would like to look to the polar direction, up, instead of through the stuff here. But to date, because of the fact that we had to write our proposals for funding to the Swedish Space Agency, I could not make this computation. I hope I would be doing it. What it would mean actually to look through through our zodiacal chart at this object with the mission, with the Darwin mission. I have to excuse myself. I can't give you the numbers. I think that the planet is, it's not the planet itself, it's the contrast between the star and the planet is still favorable enough that it would be relatively easy to see the star. But this has to be quantified. I can't do that. But if you want to read more or learn about more and keep updated with extrasolar planet research, this is a very nice thing to go for. This is continuously updated. You know how many planets there are and what's the status of them. So coming to the conclusions then, I talked much longer than I thought, is that we can summarize it as based on a radial velocity curve for the BY Draconis variable H or Libra, the existence of 3 planets is deduced, one of which is most Earth-like 2-day planet, which is inside the habitable zone of an embryo. And possibly, at least according to the authors, as liquid water and atmosphere and life on it. I feel it's more, to some extent, a feather and not a hen net. In order to get the chicken, we have to do something. I think I stop here with a little announcement, and that has to do with my personal move to Chalmers in the middle of August this year. Thank you for your attention. Oh, you get some beer. Or you want some questions first?
Yeah, maybe. One thing, it sounded like when we looked at these CO2 spectra for the 3 terrestrial planets, which is in our system with the atmosphere, they all were rather similar. I would have somehow thought the CO2 spectrum should be less prominent for the Earth, but that's obviously not the case. It
So
seems.
they're all saturated, so that's
Yes,
that's the
yes,
thing.
of course, yeah. So they,
I think it is the simplest,
So what is then
biggest
the,
answer.
yeah, but if you have that, can one actually see something very quickly? What is the main, the ozone, yeah? Ozone and water.
What the astrobiologists take here as evidence for life on Earth is the simultaneous occurrence of water feature, of oxygen, and of CO2. According to these people, you need all three of them.
Mhm.
One is
Yeah.
not enough. Okay. So it's a logical and in between them. We have water on Mars. You can't see it here at this resolution, at this sensitivity. We would never pick it up. But at higher resolution, you can see water. You can see ozone. You can see oxygen in the atmosphere of Mars. But these are tremendously minute trace molecules which you would never see in distant objects.
But how can they say possibly has water?
Sorry?
How can they come to the conclusion that this planet possibly has water? That was on your conclusion.
You mean they must have meant
Yeah, but
liquid water.
it could be,
It could be, but I don't know.
possibly. It's possible. It's not
But
excluded.
that's not how you read. I mean, possibly has water. You think that there is a high probability. that it is.
No, I didn't say probably. I said possibly. According
The
to
way I read it, I mean, it seems like a very big jump.
But didn't you hear that ESA is having trouble with funding? So we should promote this.
I mean, they clearly mean liquid water on the surface,
Yes,
of
sure.
course. That's the point, I suppose.
But I mean, it was a big thing when they discovered water on Mars. It was the scientific breakthrough of the year in 2004. So.
No, but the water on Mars was not long before that.
1947.
Yeah, something like that. It's an old story.
So why was it such a breakthrough in 2004?
The same thing.
They knew where it was.
VR machinery.
Yeah.
I think so.
Oh yeah.
Yes.
Yeah, it's the same with the sun. We got a message a few years ago that there's water in the sunspots, but that was discovered in the 70s already.
Mhm.
So,
No, but you were 47, you're referring to in the atmosphere.
Yes. I mean,
But this was on the surface.
was the enormous amount of frozen water. Yes. Yeah.
I mean, that was discovered.
That is yes. Yes.
No, I personally would also agree with you that the word possibly is too strong, yes. But I was deliberately provocative here. Because that is what I think I interpret now, given the text, given the evidence of the paper, that is what somehow they wanted to speculate on that, although they had no clue at all.
Well, it's the most likely to have water so far.
Sorry?
It's the most likely to have water so far. That's what makes it interesting.
No, I don't agree.
You
Why?
think that there are other planets that are more likely to have water on them?
Why not? In the end, it depends on the amount of atmosphere you have, what the pressure is, what the phase diagram of the water looks like. I don't know. You could have it about a moon of one of these giant planets which are in there. A moon of the size of the Earth, two Jupiter mass, giant planet at a distance of 1
Yeah, but those we don't know about. I mean,
No, I'm saying...
far be it for me to talk to my journalist hat on, but of the planets that we know of and what we can identify so far, this is supposed to be the one which is most likely to
Yes.
have, which isn't saying very much. I think that's
No.
that's the important
Now it's
point.
like if somebody gives you a ring of silver and says this is the most gold-like metal I can present you. It's not gold. And it's not worth it. In that sense you are right. And if you want to, as I presented, it is likely, at least last week, the most Earth-like planet known today. But it is not very Earth-like. That is my conclusion. I haven't even addressed the way that how they got the radius of the thing. This is a somewhat, this is entirely based on models.
So considering this microlensing detection, taking into account the error bars, would you consider that one to be at least as Earth-like as this one, or even more?
And, because we don't know at what distance it is from its star, you see. That's a major problem with this thing. Sorry?
There is no psi-9 independence, so they have a better hold on the mass.
No, but you don't have the period. Yeah, you don't have the psi-9. No, the mass is okay. If you
So the mass is even better determined a year ago for this particular.
I would think so, yeah. And they give, I mean, they are very generous in their error bars. I think what they actually also write in their title is something like 5.5 plus 3 minus 1.5 or something like that. So there's quite a range that they write. But again, it's and what you don't know is how far it is away from the star. You see it in projection along the line of sight.
But I thought they did talk about a large distance and speculated that the temperature would be below 200
Yeah, I know.
centigrade minus.
I don't remember what this is due. Was it I don't remember the details, I must say. I remember
I thought they actually
they
do
were
get the
talking
ranges
about,
of this.
yeah, there was something about the distance of the order of like Pluto's.
Yeah, right, yeah.
I don't remember the argument. I think the argument was quite weak. At least they didn't push it inwards. They were quite restricted in their...
I thought it was simply a result of the analysis. I mean, I looked up the Nature paper and there was a number. Didn't check.
It depends on what you assume for the host star of the planet. Because that is not entirely known.
Right.
Whether it depends on the mass of the host star, because what you see, of course, is the transit of the thing. This gives you some information.
Yeah.
And you know that the inclination is low. But what the distance is must depend on the star. The star is not very well known. It could be anything between F and M.
And so the value that was encoded was the m sin I value. And so, what did you say? This 10 Earth mass is a magical number. Why is that? I mean, that would still imply that there might be water, right? Equally well than for 5 Earth mass planet.
Yeah, the people who are talking about water planets, they are very anxious not to go above, say, 5 solar.
Right. Why is that then? Why is that?
Because of the problem with the runaway accretion you hit in a typical nebular environment. The gas is attracted to the object, and once it grows, it goes over a critical mass limit, and then it accretes everything in its surrounding, and is doomed to become a giant planet.
Yeah, but this one has now, of course, saturated at 10, if it's 10 or whatever it is, 5.
Yeah, it's not excluded.
Theoretically, you may have expected this is not easy to make, but in that sense...
No, it's not excluded at all. No. I'm just saying...
Two other planets in the same ballpark of 10 Earth masses in the system.
Yes.
The one was 8 and the other is
17, yes.
16, 17.
Yes, right, yes.
Why? I don't know.
Yeah, but I mean, he's basically saying there's maybe no problem yet with this catastrophic accretion scenario. Maybe that's not happening.
Yeah, but in this case it's so different. The one thing which is sure is that this planet, regardless of how it formed, could not form where it is observed today. It's impossible. This is like totally impossible, because this is a small star, you're very close to the star, so even a very optimistic estimate of the proto-planetary nebula at this distance, there is not enough matter to have like even 5 Earth masses. This thing must have formed further away in the system, if it ever formed at all, the way we think it formed. But even 5 Earth masses where it is, it's impossible to form it where it is.
Based on
on the
The theory of
assumption
permanent formation.
If you assume that this thing formed out of a protoplanetary nebula, which like the ones we see around circumstellar disks, and if you look at the amount of mass which is available at this distance, the density is high, but the distance is so small that just the volume available to form a planet there is not big enough to have 10 Earth masses of solids, for instance. There, it's impossible. You have to go. If you play this game with the Earth, this is called minimum mass solar nebula. You take Mercury's mass, Venus mass, Earth mass, and then you break it into small pieces and you smooth it out, and you have this slope. What is the minimum mass for this solar nebula? And if you play the same game with this planet, even Mercury, where it is, it's a small planet, but it's further away than this guy. So you would have an unrealistically high density in this nebula. So somehow it must have formed somewhere else, which is not a big problem because everybody believed that all the hot Jupiters would form further away. But
What about, do they have any estimation of the eccentricity?
There were running two models. One was a circular case, 3 planets, and one was eccentric.
Yeah.
And they were about the same. So, which is, I can't say very much more. If you look at the table, there were 2 times 3 columns, one which was for the circular case, but the main conclusions were very similar. It's on the decimal digits, some changes, not really alarming, which is strange, I think. It should be bigger. But it tells me that the symmetry noise maybe is not sufficient in order to distinguish between the circular and the eccentric. So much more. Would you agree?
right. Yeah. I'm not a specialist.
No, I think they made a tremendously good job. The observations are first class, absolutely the best in the world. However, I think the wish to, I don't know, maybe they were also in the phase of writing their funding proposals or whatever. I think it got a little bit too far, actually. And it was, of course, taken up by journalists around the world and made into a big story. And we should be happy because we get visibility, we are exposed, and we should, of course, support it and not publicly have a scientific discussion about it, but I think that this scientific discussion is needed. Right? That was the purpose of this afternoon. But when can we have a beer now?
Thanks very much.